So we are into quantum coding theory or error correcting codes. And we have seen that if you have a channel or a storage mechanism in which you can have only bit flip errors, then that can be corrected by encoding the qubit as A0 plus B1 is encoded into this plus this. If I do this encoding, then I will be able to store this. I will be able to, if an error happens, I can restore the original qubit, provided out of the 3 physical qubits, there can only be 1 qubit that will have error or none. Yes, this was the and so you can call this the 3 qubit bit flip code. So of course, and this is the, so this, the error is that 0 becomes 1 and 1 becomes 0. This is the only thing that can happen in a quantum storage device, but in a quantum, in a classical storage device, but in a quantum storage device, there are other errors that can. So this is of course not the end of the story, this is sort of the beginning. So we will still not go to the general case. We will now assume that we have another type of a channel, another storage device, in which there is a different type of error. This bit flip error is not there in that channel. It's a different error that happens there. It's called the phase flip error. And we will try to see whether we can handle this. So, phase flip takes, so we still have our original qubit like in the previous case. In the previous case, the error that could have happened was this would go to A1 plus B0, but in this case, this is taken to A0 minus B. This is the phase flip error. So we'll try to see whether we can handle this error. So the bit flip error is no more there. This is a different type of an error. Again, this is a very concocted case. It is a non-realistic scenario. In a generic, in a realistic situation, you will have mixture of all this. We'll come to that later.
So there can be, in general case, just a phase shift.
Pardon?
Rotation.
Pardon?
There can be just a phase rotation.
Yes. So those type of things are also there. Yes. So those we have not yet considered. These are all finite rotations. You could have infinitesimal things as well.
This is like complete pi rotation.
Pardon? Yeah. This is a finite amount of rotation.
What will cause phase flip?
It depends on the physical device. The short answer is I don't know. So I'm trying to remember.
There is a nonlinear crystal, right? That fits the polarization of the photon.
Yes.
In one direction.
I don't know. Yeah. So, but I mean, this changes from system to system. How these errors happen? It changes from system to system. There is no uniform thing that happens in all this. But it does happen in many devices. So first of all, the previous one, the bit flip error, did have a classical equivalent. This led us to consider, I mean, this 0 going to 1 and 1 going to 0 has a classical equivalent, in the sense that this is essentially the only thing that can happen in a classical case. And then we could use some, because we have a classical error correcting code as well, and we could use some intuitions from there to handle this error when it happened in the quantum case. This one, however, this is no classical equivalent. I mean, there's no meaning of a bit going to minus of a bit. It doesn't make sense. So, classical intuitions seemingly will not work here. But we will actually use a classical intuition. How? However, if we consider the plus minus basis, so plus minus is the so-called x basis, yes? In this basis, the phase flip error, this error, behaves as a bit flip. Why? Because under phase flip, the plus goes to minus and the minus goes to plus. The phase flip is 0 goes to 0 and 1 goes to minus 1. So if you do that with this, you will see that they go to each other, which is very similar to what was happening in the bit flip case. The basis was getting flipped. So, the coast is clear now. We will replace all zeros and ones by pluses and minuses, and the thing will go through. But you have to know that the bit flip is not happening. It is only the phase flip happening, and then everything will work.
So this error is arising due to the incorrectness of the quantum channel. So why is it sensitive to a particular basis? Why would it?
No. So we are not assuming that this is realistic. I'm just assuming, suppose this is happening. In a realistic case, this will actually not happen. We will have a mixture of all of them.
I'm saying the input, it should not depend upon the input basis at least.
No, it doesn't.
What happens to us?
So the input basis, it can sometimes depend. I mean, it depends on the exact measuring apparatus, the exact physical system that you are using. I mean, we never see a superposition of a live cat and a dead cat because the nature seems to believe in a particular basis. Why it does so, we don't know how it happens.
So changing the basis is just like changing the interpretation of the time period.
So this takes us into philosophical questions. So I mean,
I'm just getting this from the example that by going to plus minus basis, what we were saying that the phase was flipping, here the bit is flipping.
exactly. So for small systems, the Hilbert space does not distinguish between any basis. I mean, all the bases are the same. As far as I know, for typically quantum systems, which are typically small, in those systems, all the bases are seen by nature within inverted comma in the same way. For big systems, it somehow seems that nature favors some bases. Why that is so, it's not clear. I mean, it depends with whom you are talking to, whether it's clear or not clear, and what is the answer, and also this is a controversial area. So, but we are here thinking about using it in a quantum device. This will typically be small. So there we are guessing, unless there are some device-based biases, all the bases will be. I mean, you have chances of having errors in everything. But there could be some device-based things that in some, maybe in a superconducting device, in that particular device, the basis you have call 01 has more option of getting an error than the other because of the way you are prepared. If you create that same thing by a photon, it could be in a different basis because you have called something as the basis, and the device somehow knows that. In the sense, the device has its own bias in which it was prepared. So there could be options of some of the bases being more decoherent than the other.
This is just a convenience, right? We are changing the basis so that it becomes more convenient for us to get rid of the error, just like.
You mean this thing? Yes, yes.
Yeah.
Yes, this of course is completely
I mean,
mathematics. I'm talking about why is this error happening and not the bit flip error happening, and so whether in a particular system a bit flip error will happen or a phase flip error will happen. This will, so in our theory, this will be immaterial. We will be able to consider all types of errors, all types of limited amount of errors, but all types. So it will be, so here we are considering of the 3 qubits, at most one of the qubits are in error, the others not. But any type of error, finally we will consider. Until now we have considered bit flip separately and phase flip separately.
Is the reverse also true that the phase bit flip of 01 is phase flip of +1? And the classical equivalent of plus going to minus, can that be related to taking 2's complement?
Once more?
2's complement.
2.
2's complement. Like it is.
What is 2?
It is changing a number, a binary number, to its negative. Like +10 will go to -10. That.
No. We are with a bit. It's just a bit. I didn't understand your question.
The 2's complement is it converts a positive number to negative number and vice versa.
Yes. Where is the negative number here?
Like you were saying, like that +1 bit, the +1 is the phase is changing from plus to minus.
So this 1 is just a notation. You can call it red and blue. Minus blue doesn't have a meaning. It's the minus blue that has a meaning. Just minus blue doesn't have a meaning. This is just a name. You can call it girl and boy. That's also just two orthogonal states. So of course, I mean, I will let me do it, but you realize that everything will go through. So the encoding, instead of being with A000 plus P111, now you have to encode in A plus 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 B minus and everything will go through. Yes. So, but let's do the formalism because this will be needed. So this suggests the logical thing as plus 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 and the logical one as minus. So we encode this as a corresponding circuit to prepare this from this. You have the psi, this is our psi. And these are the initial states of the two extra auxiliary parts. You apply the C0. The C0, remember, was denoted like this. And you put Hadamard salt. And the state that you get here is this. So the state that you get here is the bit flip code. Put an extra Hadamard phase flip code. So again we assume that there is a phase flip in at most one of the qubits. So, after the communication or the storage, the 3-qubit state lands in the 4 options, yes? So, if there is no error or you have error in first qubit, second qubit, or third qubit, correspondingly you will have, this is the initial thing, it goes through the channel or is stored in a device, and if of course there is no error, is even the same. If there is an error in the first one, it becomes plus 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 b minus here, right? So it's plus minus plus plus b minus plus minus, yes. And here it is a plus plus minus plus b minus minus plus. It's the same thing as before, you are just replacing zeros and ones by pluses and minuses. We have to do the syndrome diagnosis. And this can be done by the same measurements, but azimuth rotated. Everything is azimuth rotated. That is, we first measure in initially it was just in the bit flip error case it was ZZ. You have extra azimuth rotated. Everything is seen in a different from a different perspective, different basis. Which is just H2 on what we already had, which was 0, 0, 1, 1, sorry, 0, 0 plus 1, 1, 1, 1, minus and this entire thing azimuth rotated. There is of course an identity operator on the third qubit that we are doing nothing. So this was on only 1 and 2, which will be just this with 0 and 1 written as plus and minus. So plus 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 minus 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 and minus you of course realize that is just sigma x. So instead of ZZ, you are measuring in XX. But it is good to think of it like this because, as we discussed before, in a circuit, I mean, the way that you will actually do the measurement will do on the exact physical implementation, the physical substrate. But typically it is considered by many people, Marmin for example, and many others, that you should think always in a single basis. Otherwise, there could be hidden costs involved in the circuit that you are not considering. So we start everything, of course, this is the thing that is given to us, but anything else is in this basis. And at the end, we always measure in one basis. So we are considering that we are measuring in this basis, but this Hadamard rotation, you do it before that. So So I'm not writing, there is another measurement that has to be done, so I'm not writing it. Right? So with the other measurement, you will finally be able to find out which one has happened, just like in the previous case. And once you find that out, you can do the opposite of this circuit to come back here. First of all, you have to correct the error in the qubit where the error has happened, and then you apply the inverse of this circuit to bring it back to the original. Fine. Any questions?
So like we assume that no matter what density matrix you write down on paper, you can probably recreate it in a lab by like whatever mixture you want. Do we also in some sense assume that once you write down a POVM, like a complete set of measurements, you can also implement them in the lab in the sense because how do we know that whether the measurements are allowed?
Yeah. Where did you see a POVM here?
Like higher order, we are creating higher rank measurements here.
Exactly.
But we can.
This is a projection operator. This is, I mean, a POVM. Every PV is a POVM. So these are all projection operators. These are higher rank projection operators. Whether we can actually do the measurement, of course, is a different question.
POVM can be created even without just considering projection operation. We can consider an altogether complicated set of operations.
Yeah.
So
it has to be positive operator.
Yeah.
One has to act to unit.
Yeah. So how do we actually implement it?
Yeah, this we don't know. This is not known. So finally come to the short code given by Peter Shore 5. So the question is whether we can protect a qubit from more general errors. Yes. So to be sure, there are more general errors. Yes, I mean it's not only bit flip and phase flip that happens in a channel. I mean one can have sigma y. That's of course the next thing, but that you can handle in the same way. Or you can have like 0 going to 1 and 1 going to something like 2 pi by 29 1, yes? You can have anything, as Divyansh was mentioning, that it could be some small change that can happen. And there can be many others that could happen. So we will do the thing in steps. We will first assume that the communication channel has a bit flip as well as a phase flipper, and see whether that we can correct. It is not a, so what we will assume, we now try to see whether we can protect a qubit from bit as well as phase flip errors. This is not what is called bit and phase flip error. Yes, this is not A0 plus B1 going to A1 minus B0. This is just sigma y up to a phase. We are not talking about this. We are talking about in the channel there may appear a bit flip error or there may appear a phase flip error. We don't know which one is appearing. So this is not the case that we are considering. This is just sigma y. This can be handled in the same way we changed from the bit flip to the phase flip. This can be changed in the same way.
So if the error is non-unitary, if the channel is non-unitary, then we cannot always correct the error.
Error is non-unitary.
Yeah.
Errors are all unitary.
No, take the second one. 0 goes to 1 and 1 goes to
It is unitary.
Is it unitary?
It is. Any basis going to another basis is a unitary operator.
0 is going to 1 and 1 is going to 1.
Oh, sorry. So Z. This is a typo.
But we can have non-unitary error.
No.
Channel can take
We are restricting ourselves to that case where the transmission is only unitary.
No, that's the point. What I'm trying to say that all errors are unitary.
At the point of
I mean, you believe in quantum mechanics. So, I mean, it can be that you need an auxiliary system and the error is happening on a bigger system. And then on the smaller part, it will be non-unitary. But as a whole, it will be unitary.
In the end, the information that we are transmitting can have non-unitary error.
In the channel. But I will consider the environment in my picture and consider that whole thing as the channel, and then it will be a unitary error.
Can it always be done?
Can it always be done in what sense? In the sense, if you want to say it's experimentally, it can never be done.
Yeah.
Almost never be done. In the theoretical sense, it's a belief that we can do that. That is what we assume in quantum mechanics. come to more general errors actually, where you need an auxiliary on a bigger, unitary on a bigger size. So, as I said, this is not something, this is called a bit phase flip error, which is just sigma y. Up to a phase. So, in this channel, the channel that we are considering, this is still far from the, not so far as you will see, but a priori it seems to be quite far from an actual realistic channel. One can sometimes have a bit flip error and sometimes phase flip, and a priori we do not know which one has power. Yes, this is the situation. So we have gone to seemingly more general, but not the most general type of error in the channel.
Only one of the phase flip is.
Yeah, so we considered these separately. We considered channels where bit flip and phase flip are happening separately, and now we have a channel in which any one of them can happen. But we don't know which one has happened.
We were also restricting that if we throw inside 3 bits, only one will get hit.
In this one, it's more than that. Yeah, so we have not come to that. We will do that. So in the previous cases, we have assumed that it was a limited type of limited amount of occurrence, in the sense that out of 3 qubits that we have encoded, only one of them at the most can get affected. Here we will again assume a limited type of error. I mean, all error correcting codes work under a certain limit. We'll see the limit in which this works. We will further assume that out of the 9 qubits, this time we will have 9 qubits in which we will do the coding instead of the 3 in the previous case. So there will be 9 physical qubits. So we will use 9 physical qubit to encode a single logical qubit. In the previous cases, so it's much more costly. If an error occurs, it occurs in only one. So this is a huge amount of limit. Is a much more stronger constraint on the amount of noise that is there in the channel. have such a channel? So once more, the channel is either the bit flip happens or the phase flip happens, don't know which, and we will be encoding 1 qubit in 9 qubits, and in those 9 qubits either nothing will happen to any one of them, or in only one of them at the most there will be a bit or a phase. In such a channel, protection against this noise is possible by choosing, and this is the short code, the 0 L, the logical 0 will be three GHZs. And the logical 1 are with the minus signs. There's sorry, there are tensor products that I have missed out, okay? Bracketed. Well, there's some algebra now. We will see why this works. First of all, the encoding can be attained prepared by the following circuit. So you have the psi, and you like this, you take two auxiliaries in a standard state, you apply C naughts, so this is the bit flip code. This is the phase flip code. Now we will put in two more qubits from here, two more auxiliaries from here, and two more auxiliaries from here. C0 gates on all of them. This will be the show code. So we will now do the syndrome diagnosis. To find out whether bit flip has occurred in any of the physical qubits we first measure on the first. So the result can be either +1 or -1.
Could you label 1, 2, 3 on the circuit?
This 1 to 9 is in the same way as there.
So by result plus minus one, you mean either both of them stay 0 or one of them flips to 1?
is no error in first 2 qubits, no bit flip error, because we are considering first the bit flip. And this implies that there is error in either first or second qubit. Again, error means bit flip. For if you obtain +1 in this, you do a sigma z2, sigma z3 on 2 and 3, and again the result is either +1 or -1. If it is +1, then no error, no bit flip error in the first 3 qubits, yes? No error in 2 and 3, but we have come from +1. There is no error in the first 2, so we have no error in the first 3. If it is -1, then there is error either in 2-3 or in 3-2. But if you want to satisfy this as well as this, it can only be in the second. No, sorry. Forget. We have come from +1. There is no error in the first 2 qubits, so it's only in third. So found the error. You don't need to go any further. Bingo. You only found the bit flip error. But we have already assumed that if an error happens, it only happens in one, so there is no need to go any further. And you know where it has happened. It has happened in the third qubit. So you apply this, sigma x, and you will get the original entire thing. And you apply an inverse transform of this entire thing, and you will land in this. For -1 in the 2, this option we had left. Do the same. The implications are different, but the measurement is the same. Again, the result is either +1 or -1. If the error is +1, we have come from -1, yes? So there is error in either first or second. But this one says that there is no error in 2 and 3. So there must be error in the first. Yes? Error means again bit flip error. Yes? You don't need to go any further anymore. That's the end of this. If it is -1, then, as we discussed mistakenly in the first case, there is error in second. And you stop again. So these 3 cases, you don't need to go any further. So the only case where you need to go further is when you have +1 here and +1 here. For these, if these happen, you need to go still further.
To check different cases, we are assuming we have multiple copies of the same system.
No. We have the same thing.
With one
So
copy,
we have to remember, so this we did not mention explicitly here. We have just a single copy.
with one go we are doing all this.
Yes, because these measurements, our state is an eigenvector of all these measurements. So it gives us the value, but it doesn't disturb the state. We are assuming repeatable measurements. So
Even the Hadamard rotated one is going on better.
yes. Nothing happens to the state. This doing it in practice can be difficult. In typical photonic devices, the state after measurement gets absorbed and lost. But we are assuming that we can do this. For sigma z1, sigma z2 equals +1, I mean equal to in the sense that in the measurement you get +1, and sigma z2, sigma z3 equals +1, we need to press far. Okay. So, but we know how to proceed, yes? So, we do 4, 5, and then 6, and so on. And go in the same way. And then we'll find if a bit flip has happened in any of the places, or maybe it has happened nowhere. We'll find that out by doing this procedure. We'll have to, so in this case also, you will have something like this, and you will have something like this option. You have to go to the 7, 8, and 8, 9. And that will be there. So, you have to do that. In the end, meaning after doing the 7, 8 and 8, 9, any bit flip error, if present, will be detected. And moreover, encoded state, does not change in the entire process. Fine. So this was only bit flip errors, but this is not only what we are after, right? With bit flip errors, we know that we can do it with more noise and with 3-qubit code. Here we have assumed only one of 9 qubits that will be in error at the most. But of course, there could be phase flip errors, and this we haven't settled as yet. We don't yet know whether the state that we have got through this entire process has a phase flip error in the encoded system. So we will now study this now for the same code. We will now try to see whether, if a phase flip has occurred, whether we can detect it and correct it.
Since we are sure that bit flip is not there, so we can
So
just repeat the procedure we just previously studied before the short code.
No, but because here the encoding is different. So here you see that the phase is inside a GHZ state. It is not in every qubit. So the syndrome analysis for the phase flip will be different here, not the previous one. Pardon?
We can do something like 147, 258, and
Yeah, we will have to use
6.
3-qubit measurements to get the phase flips. So we first note that a phase flip error on any of the first 3 qubits, there are 9 qubits. If a phase flip error happens on any one of the first 3 qubits, changes 1, 2, yes, and vice versa. This tends to this, this tends to this. In the first block, remember the shore code? The shore code was, there was 0, 0, 0 plus 1, 1, 1, and there was another, I'm not writing the normalizations, and then there was a minus. So this is the first block of 3 qubits. Here, if the phase flip happens in any one of the qubits, you will, this will be transformed to this and this to this. Similarly in the other blocks. if such a thing has occurred, this type of a thing has occurred, it can be diagnosed by a measurement with the projectors put a new notation here, so it's this plus tilde is the GHZ. Plus minus tilde is the minus GHZ. So this is the minus 1. So this is not a 2 qubit but 6 qubit thing on which we measure, call it 1 tilde and 2 tilde, where this 1 tilde is 1, 2, 3, 2 tilde is 4, 5, 6, and we will have a 3 tilde, which is 7, 8, 9. Tensor nothing on the other 3. So this is one of the projectors in the measurement, and the other one is plus minus, yes? But with tildes everywhere. We will do this measurement, and you can check, take some algebra to do that, but you can check that by using this, you'll be able to find out. The main thing to recognize is that if you think of this entire thing as a 0 and think of this entire thing as a 1, then this, the entire thing becomes a 3 qubit phase code, phase flip code. There, you remember that we had done this measurement exactly, where these were single qubits then, now these are 3 qubits. So if you remember that, then this becomes obvious.
Is this also then hardware tensor 3 sigma x tensor 3 hardware tensor 3 sort of?
No, this cannot be prepared locally because GHZ states have entanglement within it.
This
Generally,
projector is not.
you cannot do it that way, then you see not get involved inside it. So this hides more difficulty inside it.
Also, at the end, we'll only get to know which set of 3 qubits has the phase flip.
Yes. I'm coming to that, yeah.
So, two tilde, three tilde, and identity in one tilde.
Exactly. So, exactly, yeah. So it can be in 1, 3 as well. So I have been doing it as 1, 2 and 2, 3. But you can do it in any 2 and any other.
Last, you do one, 2, and 3.
So this is not the end. This is one measurement, but if you remember the phase code, the phase flip code, there you do in first in this two and then in this two. Yeah, you could have done in this two as well, but you do this two and this two. So this one is this two. You have to follow this up with this two to find out where exactly the phase error has happened.
Instead of a comma, you should plus or minus something.
Pardon?
Like in the normal 3-qubit code, we have plus plus, plus minus minus projector, minus plus minus, and minus plus projector.
Yeah. So there I was writing the operator, whereas here I'm writing only the projectors. I have not yet written the eigenvalues. So if you want, you can consider this as eigenvalue plus 1, and this you can assume value minus 1. So as you know, the eigenvalues are not physically important. It's a bookkeeping strategy. It's the projectors that are physically relevant. You can give it +5 and -5, it doesn't matter, or roses and whatever, lotuses.
Is there any, I don't know if this is a relevant question, but is there any deeper reason why we're considering geodesistic? Why should we involve entanglement? Why should we, why couldn't we have
Can we do it?
two local operators? Is there not a better way? That's my question.
You said like
There is a better situation in the sense that you can do it with 5 qubits. The CSS codes are using 5 qubits. But they are, of course, pardon? CSS codes. Calderbank Shore Steam code, and this is the best that you can do, 5 qubits. You need to store a single qubit, but they are also very entangled. So I don't know whether people have worked in this area, whether there is a minimization of the amount of entanglement content of the error correcting codes. I don't know of any work in that direction. There is a very old work by Vivincenzo and Perez where they show that these codes violate some multi-qubit Bell inequality. That is the only thing that I know.
So they consider the same error class, either one bit flip or one phase flip, in those 5 qubits that they are transporting.
Forgot. I don't know. I think it's one of the 5 qubits is in error. As per I don't remember this, but I think the same. So once more, if such a thing has occurred, it can be diagnosed by a measurement on these projectors and put a comma there, followed by a projector of the same thing, but with 1 tilde, 2 tilde, 3 tilde replaced by the non-trivial part is in the 2 tilde, 3 tilde part. So from there, followed by a measurement where the non-trivial part is in 2 tilde. And just like in the previous case, it always remains an eigenvector of the measurements. And after finding the error, remember we have found out whether the error is in the first three, the second three, or the third three. We don't know where, but we don't need to. Once you have found out, suppose it has happened, you have found out that the error has happened in the second block. You apply a phase flip in one of the physical qubits and it will correct the error without knowing where it is occurring. So, I'm not writing that. Local with respect to physical qubits, not with respect to blocks. Local meaning single qubits, single physical qubit.
But we don't know the value of how much we have to flip it. Like in the expert you wrote in starting in the second line, e raised to or something.
No. So that was an example. We have not considered that error. So this is the channel or a storage device in which out of 9 physical qubits, either there is no error or in one of them there is either a bit flip or a phase flip.
Phase flip of pi. And here why we put a restriction that both bit flip and phase flip can't occur together, because like if we have detected the bit flip, we can always correct it and then apply this phase flip algorithm.
We will come to all those. Yeah. So, but here we have this restriction that in one of the things it has happened. There's still 2-3 pages. We'll do it next week.